Africa is not as solid as it looks. Across the eastern edge of the continent, the ground is slowly pulling apart, measured from space in movements so small they would be invisible beneath your feet. But this is not simply a crack in the landscape. It is the beginning of something much larger. In 2005, more than 420 earthquakes struck northeastern Ethiopia within a matter of weeks. When the activity subsided, a fracture roughly 56 kilometers, about 35 miles, long had opened across the desert floor. Scientists who arrived to examine it were looking at something unusual, not just an earthquake sequence, the early stages of a new ocean. The landscape surrounding it makes the idea even harder to imagine. The Danakil Depression lies more than 120 meters, roughly 400 feet, below sea level, surrounded by acid pools, sulfur chimneys, and ground hot enough to make the region one of the hottest inhabited places on Earth. And beneath all of it, three tectonic plates are pulling away from one another. The process has been unfolding for millions of years. It is the same fundamental process that once separated Africa from South America and opened the Atlantic. This time it is happening beneath Africa itself. The continent is not breaking apart in some distant geological future. It is already happening, and the ground where some of humanity's earliest ancestors once walked sits within this enormous zone of change. The landscape looks permanent. It isn't. Today, we're going into the heart of East Africa to follow the fractures, earthquakes, and shifting plates that are slowly pulling a continent apart. Before we go any further, if this is the kind of content that keeps you curious, take a moment to like the video and subscribe. It helps us keep bringing these unusual corners of Earth's story to you. Now, let's step into the landscape where Africa is beginning to come apart. To understand how a continent can come apart, it helps to first loosen the idea of a continent as something fixed. The land beneath our feet feels permanent because human lives occupy such a narrow slice of geological time. Earth sees the surface differently. Continents are arrangements of rock carried across a restless planet, assembled, reshaped, and separated as the interior continues to release its stored heat. The outer crust is only the skin of this structure. Beneath continents, it averages about 25 miles thick, while oceanic crust is much thinner, averaging about 4 miles. Below the crust lies the mantle, a layer of solid rock extending roughly 1,800 miles toward the center. Although solid, the mantle can deform and flow over immense spans of time. Far below that lies the core, dominated by iron and extending through the planet's deepest interior. The crust itself is divided into large tectonic plates, generally counted as around 15 to 20 major plates, along with numerous smaller ones. They are always in motion, although their movement is far too gradual for a person to notice from one day to the next. Heat escaping from Earth's interior helps drive circulation within the mantle. Warm material rises, cooler material sinks, and this immense transfer of heat contributes to the movements of the plates above. That motion has been rearranging the continents for billions of years. Earth has repeatedly gathered its land masses into supercontinents, then pulled them apart again. The interval between major supercontinent assemblies is commonly estimated at roughly 300 to 500 million years. This cycle has been operating for at least 3 billion years, long before animals walked across recognizable continents, and long before any human could imagine a changing world beneath them. The most recent great assembly was Pangaea. It had become largely complete by about 299 million years ago, bringing nearly all major land masses together into one enormous continent. Around 200 million years ago, fractures began opening through that joined landscape. The pieces gradually separated, oceans widened between them, and the geography familiar today emerged from that prolonged rearrangement. Continental breakup begins with a process called rifting. When forces within the planet stretch a section of continental crust, the surface can rise, fracture, and sink along enormous faults. Magma may ascend through the weakened rock, feeding volcanoes and adding new material. As stretching continues, the continental crust becomes thinner and the depression grows deeper. Eventually, if the rift succeeds, seawater can enter the low basin. New oceanic crust then forms as molten material rises and hardens along the center. The Atlantic Ocean records this sequence on a grand scale. Its floor began developing after Pangaea started to separate, through the same fundamental combination of stretching, fracturing, volcanic activity, and seafloor spreading. What now appears as an immense blue divide between continents began as a geological disturbance across a connected landmass. East Africa is therefore part of a familiar planetary rhythm. The process unfolding there belongs to the same family of events that has repeatedly changed Earth's map. The remarkable part is the timing. For the first time in human history, instruments can measure a continent while it is entering this process, allowing us to observe the earliest stages of a transformation that usually survives only as evidence in ancient rocks. September arrived in the Afar Depression with a disturbance that grew by the day. From the middle of the month into early October, hundreds of earthquakes passed through the region, including many strong enough to register clearly across surrounding landscape. More than 400 seismic events were associated with the crisis, while 15 earthquakes exceeded magnitude 5. For several weeks, the crust seemed to be answering the strain accumulated across the rift. Then the pattern changed. A section of the Dabahu Rift, roughly 60 kilometers, which is about 37 miles long, began to open across the desert. Satellite measurements later showed that the ground had separated by as much as 8 meters, which is about 26 feet, along parts of the rupture. The scale was striking, yet the greater significance lay in how quickly it happened. A geological structure of this size could develop through ordinary fault motion over centuries. Here, much of the major opening occurred within a few days. The force came from below. Magma had gathered beneath the stretched crust and then entered a long vertical sheet called a dike. The molten rock pushed its way through the brittle material, forcing the surrounding crust apart. The intrusion extended from depths of about 2 kilometers, which is about 1.2 miles, to 9 kilometers, that is nearly 5.6 miles, below the surface. Roughly 2.5 cubic kilometers, which is about zero point 0.6 cubic miles, of magma entered the crust during the main episode. That molten material behaved like a wedge moving through a solid shell. As it advanced, the rock on either side responded through fractures, fault movement, and gradual changes in elevation. Seismic shaking accompanied the intrusion, yet the earthquakes accounted for only a small fraction of the total deformation. Most of the separation came from the magma itself, stretching the rift from within. The event gave scientists an unusual opportunity. Radar observations from satellites could compare the shape of the land before and after the intrusion, while positioning instruments on the ground recorded changes in distance between fixed points. The measurements revealed that a rift segment had ruptured on land on a scale rarely witnessed by modern geodesy. When the findings appeared in Nature in 2006, they showed that continental rupture could unfold through concentrated pulses of magmatic activity rather than through an even, continuous widening. That distinction changed the picture of a continent breaking apart. A rift can spend long periods accumulating strain, then release part of that strain through a rapid intrusion. One episode can be followed by another, with each injection finding pathways through rock already weakened by earlier movement. After the main crisis, additional magma intrusions continued along the same rift system in the following years. The ground left behind in 2005 therefore became more than a fracture across Ethiopian desert. It became a physical record of a continent responding to forces beneath it. The opening measured only a few meters at the surface, yet the process reached kilometers into the crust and involved enough molten rock to reshape an entire segment of the rift. For those watching from instruments on the ground and in orbit, continental separation had acquired a new quality. It could be measured while it happened. The fracture remains part of a network extending nearly 4,000 miles through eastern Africa, linking separate rift segments. Deep under Africa, the source of the movement is measured in a place no human instrument can reach directly. The boundary between the mantle and the core lies about 2,900 kilometers, which is about 1,800 miles below the surface. There, heat has been moving through the planet for billions of years, carried by material that rises and sinks within the mantle. One of the largest clues to this deep circulation comes from seismic tomography. Earthquake waves travel through the planet at different speeds depending on the material they encounter. By comparing those changes across many earthquakes, scientists can build images of structures buried deep inside Earth, much as medical imaging can reveal structures within the human body. These images show an enormous region of unusual heat beneath Africa, commonly called the African superplume, extending upward from the deep mantle and ranking among the planet's largest deep thermal anomalies. Its influence reaches far above its origin. Hot mantle material rises toward the base of the African continent, transferring heat into the rock above. The overlying crust responds by swelling upward across broad areas, helping explain why the East African landscape contains high plateaus and elevated mountain regions. The surface elevation is therefore connected to activity occurring roughly 2,000 kilometers, which is about 1,200 miles below it. A raised region of crust carries another consequence. Once the center of a continental dome becomes elevated, gravity encourages the surrounding slopes to spread outward. The crust is stretched from several directions at once, placing it under tension. Faults open, blocks of rock move downward, and the continental shell becomes thinner. Each fracture creates another pathway through which magma can rise, allowing heat from deeper levels to reach closer to the surface. Measurements across the most active parts of the East African Rift reveal how far this thinning has progressed. Continental crust commonly measures about 40 to 50 kilometers, which is about 25 to 31 miles, in thickness. In parts of the rift, geophysical studies indicate thicknesses of roughly 20 kilometers, which is about 12 miles, or even less in the most advanced areas. With so much rock removed from the original thickness, the mantle sits considerably closer to the surface. A second force enters from the north. The Arabian Plate has been separating from Africa for millions of years, opening the Red Sea and the Gulf of Aden. As Arabia moves toward the northeast, the surrounding crust experiences additional tension. That stress travels into the Afar region, where the northern rift systems meet the developing East African separation. The deep heat and the regional plate movements therefore work together. One influence rises from Earth's interior, warming and lifting the continent. Another acts through the motion of neighboring plates, stretching the crust across the surface. Neither force needs to operate like a single, sudden shove. Their effects accumulate through countless small movements, interrupted by episodes when magma enters fractures and the ground responds much faster. Across eastern Africa, the landscape records this partnership in elevated plateaus, faulted valleys, volcanic centers, and thinning crust. The continent is being reshaped through the interaction of heat rising from deep within Earth and plates responding to the changing stresses around them. The surface carries the visible traces, while the engine itself remains far below. At the northern edge of East Africa, three immense fractures meet across a small region of desert. This meeting point is the Afar Triple Junction, where the boundaries of three tectonic plates intersect and the geometry of continental breakup becomes unusually clear. Each branch follows its own direction, yet all three belong to the same connected system of moving crust. One arm reaches northward through the Red Sea Rift. Another extends eastward along the Gulf of Aden toward the Indian Ocean. The third continues south through Ethiopia and Kenya, following the East African Rift toward Mozambique. Together, these branches form a three-sided pattern across the region, with each boundary accommodating the separation of neighboring pieces of Earth's crust. The plates themselves have distinct identities. To the west lies the Nubian plate, carrying most of the African continent. To the southeast is the Somalian plate, containing the Horn of Africa and much of eastern Africa. North of the junction is the Arabian plate. Their movements are gradual, measured in distances that would barely register during a human lifetime, yet they have been accumulating across millions of years. There is an elegant order to the arrangement. The three rift branches meet at angles close to 120 degrees, a geometry that can occur when three boundaries meet in a mechanically balanced configuration. The landscape, therefore, carries a pattern that can be described with mathematics as readily as with geology. Faults, volcanoes, basins, and plate movements all occupy positions within that larger design. The most interesting difference appears when the three branches are followed away from their meeting point. The Red Sea and Gulf of Aden have already progressed beyond the earliest continental stage. Their central zones contain newly formed oceanic crust, created as magma rises and solidifies while the plates move apart. Seawater occupies the elongated basins, giving these two arms the character of young seas. The southern branch has reached a different stage. Much of the East African Rift remains on continental ground, with elevated land and enclosed basins occupying the developing separation. The transition is therefore visible within one connected system. At one end, continental crust is being stretched. Farther north, seawater already covers crust created through seafloor spreading. This makes the Afar region an unusual geological crossroads. A person standing there is close to a boundary where two mature stages of rifting meet an earlier continental stage. The landscape does not represent three unrelated cracks. It records three directions of plate motion converging within one system, with each branch preserving a different chapter of the same physical process. The Arabian plate is separating from Africa at roughly 2 centimeters per year, which is about 1 inch per year. The Somalian plate moves away from the Nubian plate at roughly 8 millimeters per year, which is about 0.3 inches per year. Such distances seem modest, yet satellite measurements can detect them and track their accumulation across the landscape. At the Afar Triple Junction, the future geography of Eastern Africa is therefore written into the arrangement of three moving boundaries. One branch already carries oceanic crust beneath seawater. Another is expanding toward the ocean. The third continues through continental terrain, preserving the earlier stages of the same transformation. Earth has drawn three pathways from one meeting point, and each is carrying a different part of the continent toward a new configuration. The Danakil Depression gathers several stages of Earth's transformation into one basin. In northeastern Ethiopia, beside Eritrea and Djibouti, the land stretches for roughly 200 kilometers, which is about 124 miles from end to end, while its broadest reaches span around 50 kilometers, which is about 31 miles. Much of the floor lies more than 120 meters, which is about 400 feet below sea level, making this one of the lowest exposed places on the planet. Heat is part of the landscape itself. Average daily temperatures can approach 34 degrees Celsius or 93 degrees Fahrenheit, and summer conditions can climb toward 50 degrees Celsius or 122 degrees Fahrenheit. The air, ground, and mineral springs all carry evidence of heat moving upward through exceptionally thin crust. Some of the rocks exposed across the depression are basaltic, resembling the dark volcanic rock that forms much of the ocean floor, a reminder that the crust here has undergone intense stretching and magmatic activity. Erta Ale rises from this setting as a broad shield volcano. Its summit contains one of the world's persistent lava lakes, a surface pool of molten rock that has remained active through periods of observation. The volcano was first recorded erupting in 1906, and later observations documented repeated activity. At the surface, lava can reach temperatures near 1,100 degrees Celsius, or roughly 2,000 degrees Fahrenheit. The glow from the molten lake is produced by heat escaping through a crust that has been fractured and thinned from below. Farther across the depression, Dalol presents another expression of the same geothermal system. Hydrothermal fluids rise through layers of salt and volcanic material, carrying dissolved minerals toward the surface. Pools can appear yellow, orange, green, or white as different compounds crystallize and accumulate around springs. Some waters reach temperatures above 60 degrees Celsius or 140 degrees Fahrenheit, while their acidity and salt concentrations create conditions that are extraordinarily difficult for ordinary organisms. Research published in 2019 examined these extreme pools and reported that some of the most concentrated environments showed no detectable microbial life. The finding became important beyond the Danakil itself. Places on Earth where heat, acidity, and salt combine so intensely can serve as natural comparisons when scientists consider environments on Mars or icy worlds farther from the sunday. The absence of detectable organisms in particular pools does not establish that every part of Dalol is lifeless, yet it reveals how narrow the boundaries of known terrestrial life can become. The salt beneath the depression carries another record. In places, deposits reach several kilometers, which is about 2 miles, in thickness. They accumulated through repeated flooding and evaporation as seawater entered enclosed basins, leaving minerals behind when the water disappeared. Layer after layer preserves traces of changing water chemistry and shifting connections between the depression and nearby seas. For the Afar people, these geological layers are also part of everyday life. Salt is cut into slabs from the desert floor and carried outward by camel caravans toward markets in the highlands. The material being carried away began as seawater, was transformed by evaporation, and remained in the ground through immense stretches of geological time. Human hands now remove pieces of that history, one slab at a time. 500 miles north of the Danakil Depression, the Red Sea offers a glimpse of what continental rifting can become. Its waters occupy a long depression between northeastern Africa and the Arabian Peninsula, yet its history belongs to the same family of movements shaping East Africa today. The difference is measured in millions of years, not in kind. The separation began roughly 25 to 30 million years ago, when the Arabian Plate started moving away from Africa. As the crust stretched, faults opened and the land subsided. Eventually, seawater entered the developing basin, turning a continental fracture into a young marine environment. The Red Sea, therefore, records a stage that lies farther along the same geological path. Its dimensions give the basin an oceanic appearance. It extends for roughly 1,900 kilometers, which is about 1,200 miles, and reaches widths approaching 300 kilometers, which is about 190 miles. In places, the seafloor descends nearly 3,000 meters, which is about 9,800 feet. Along its central axis, however, the most important feature is far below the waves. There, an active spreading ridge adds new oceanic crust as molten material rises from the mantle and cools. Rocks recovered from the seafloor include oceanic basalt, a composition associated with newly formed seafloor rather than the thicker continental crust surrounding the basin. The Red Sea has therefore crossed an important geological boundary. It remains young by oceanic standards, yet its central floor already behaves like the floor of a developing ocean. The landscape around its southern end preserves another part of the story. The Ethiopian highlands and the highlands of Yemen contain enormous layers of flood basalt formed during volcanic eruptions that occurred before the two regions were separated. Matching ages and chemical characteristics reveal that these volcanic provinces once belonged to a connected landscape. The same geological forces that raised and fractured that plateau eventually opened water between its two sides. The Red Sea and the Gulf of Aden now form two established marine branches around the Afar region. Their continued spreading supplies a useful natural comparison for the continental rift farther south. Geological models indicate that continued subsidence and stretching could eventually allow seawater from these northern basins to enter the lower regions of the Afar Depression. The route would follow terrain already shaped by rifting, with the Danakil among the first areas affected by such an incursion. This process would resemble the birth of the Red Sea itself. Water would occupy a basin created through tectonic extension, while continued movement would deepen and widen the connection. Volcanic activity would continue along the margins, and new oceanic crust would gradually form along the center as the plates moved farther apart. Seen across geological time, the sequence becomes easier to recognize. The East African Rift represents continental stretching in progress. The Red Sea preserves a younger marine stage, with seawater and seafloor spreading already established. The Atlantic records the same fundamental process after more than 100 million years of widening. Three landscapes, separated by geography and immense stretches of time, preserve different chapters of one planetary mechanism. The sequence connects a dry continental valley, a young sea, and a mature ocean through the same patient movement of Earth's plates. There was a time when the Atlantic Ocean existed only as a line of weakness across a single continent. Around 200 million years ago, Africa, Europe, North America, and South America were joined within Pangaea. Where blue water now stretches between them, a broad rift valley crossed dry land, marked by fractures, volcanic eruptions, and basins filling with sediments. The first stages followed a sequence familiar from other continental rifts. The crust stretched and became thinner. Faults deepened the valley, while magma rose through newly opened pathways. Eventually, seawater entered from the north. Once molten rock began forming new seafloor at the center of the widening basin, the separation acquired a rhythm of its own. The continents continued drifting apart, while fresh oceanic crust occupied the space between them. Each new layer added another piece to the widening floor, preserving the movement in rock. For more than 180 million years, that opening continued. The Atlantic expanded from a continental fracture into a major ocean, carrying Africa eastward relative to the Americas and leaving a broad record of its own creation on both sides. South America and Africa separated later than some of the northern portions of Pangaea. Their final breakup began around 138 million years ago, beginning farther south before the separation extended northward. The coastlines preserve an outline of that earlier union. Eastern South America and Western Africa appear almost made to meet, especially around the curves of Brazil and the Gulf of Guinea. Their correspondence becomes even stronger when the edges of the continental shelves are considered. The match is geological, produced by two landmasses that once formed opposite sides of the same fractured region. Fossils carry the story farther inland. Mesosaurus was a freshwater reptile that lived in lakes and rivers rather than in an ocean. Its fossils occur in both southern Africa and eastern South America, separated today by roughly 4,800 kilometers, which is about 3,000 miles of Atlantic water. A freshwater animal could not have crossed that ocean. The more natural explanation is that the continents were connected when Mesosaurus lived, sharing a freshwater environment before the Atlantic opened between them. The rocks themselves preserve another connection. Precambrian basement rocks in northeastern Brazil resemble rocks across western Africa in age, mineral composition, and geological structure. These formations developed as continuous parts of the same continental foundation, then became separated when oceanic crust formed between them. The Atlantic floor now occupies the space where those connected rocks once touched. Even the pace of the transformation provides a useful comparison. The Atlantic continues widening at roughly 2.5 centimeters per year, which is about 1 inch per year. That rate is close to the opening measured in some southern portions of the East African Rift. The difference lies mainly in how far each system has traveled along the same geological path. The Atlantic, therefore, offers a finished landscape for a process still unfolding in East Africa. Its coastline, fossils, rocks, and seafloor preserve the evidence of a continent that once stood together before gradually becoming two sides of an ocean. Today, instruments can record a similar separation while it is happening, giving humanity something earlier generations of life never possessed: a direct view of an ocean beginning. South of the Afar, the East African Rift divides into two great branches, and the western one follows a different rhythm. Its valleys receive more rain, its slopes carry thicker forests, and its fractures have gathered water into some of the deepest lakes on Earth. The landscape becomes a record of stretching written in water, with each basin occupying a depression formed as the crust bends and breaks. Lake Tanganyika rests within one of these elongated basins. Its deepest point reaches about 1,470 meters, which is about 4,820 feet. The lake extends for roughly 676 kilometers, which is about 420 miles, while its widest reaches span nearly 72 kilometers, that is about 45 miles. More than 18% of the world's available fresh surface water is held within this single body. Tanganyika began taking shape between 9 and 12 million years ago. Its great depth and restricted circulation have allowed layers of water to remain separated for long periods. Far below the surface, oxygen becomes scarce, and the deepest water remains largely isolated from the atmosphere above. This unusual setting has given evolution a long interval in which to experiment. Of the 214 known fish species in Tanganyika, 176 occur nowhere else on Earth. Mollusks, crabs, and unusual jellyfish like animals add to this distinct community. Some display forms and behaviors more commonly associated with marine environments, reflecting the strange possibilities that can emerge when a freshwater basin becomes isolated for millions of years. Farther south, Lake Malawi stretches through another major rift basin. It reaches about 580 meters at its deepest point, which is about 2,316 feet, and extends for roughly 580 kilometers, which is about 360 miles. Its waters contain an estimated 800 to 1,000 species of cichlid fish, an extraordinary concentration of freshwater diversity. The lake has become a natural laboratory where isolation, competition, and changing habitats have produced a remarkable range of forms. Lake Kivu presents another expression of the same geological setting. Along the border between Rwanda and the Democratic Republic of the Congo, volcanic activity below the lake has allowed enormous quantities of dissolved gas to accumulate in deep water. Estimates suggest roughly 49.7 billion cubic meters, which is about 65 billion cubic yards, of methane and 10.7 trillion cubic meters, that is nearly 14 trillion cubic yards, of dissolved carbon dioxide are stored there. A major disturbance could potentially release that gas in a limnic eruption, a sudden and catastrophic escape of dissolved gas from a lake. Around 2 million people live along the shores of Lake Kivu, making its geology part of everyday life. Across the western branch, water has gathered inside fractures that were created by the gradual separation of the continent. The lakes also shelter evolutionary histories found nowhere else, preserved within isolated basins whose conditions have persisted for millions of years. As the rift continues its patient movement, those waters remain tied to the changing shape of the land around them. Much farther ahead in geological time, seawater may enter these basins, transforming freshwater worlds into parts of a new ocean and carrying their long isolation into another chapter. March of 2018 brought an unusual interruption to ordinary life near Mai Mahiu in southwestern Kenya. A fracture opened across the ground, cutting through farmland and reaching the Nairobi to Narok Highway, one of the country's important routes. For people nearby, the event appeared with startling immediacy. A surface that had carried vehicles and crops was suddenly divided by a fresh scar, exposing the instability of rock and soil below. Within days, the fissure stretched for several miles, with sections reaching tens of feet across. Water stained red in places as mineral-rich groundwater rose through newly opened fractures. The color came from material carried upward from below, giving the exposed earth another visible sign that deeper geological structures were involved. Seismic tremors accompanied the disturbance, consistent with movement along faults or the intrusion of magma at depth. Rainfall was initially offered as the explanation. Heavy rains had saturated the ground, weakening soil and allowing part of the surface to collapse. There was truth in that observation, because water can destabilize loose material and expose fractures that had remained covered. The deeper story, however, reached into the architecture of the East African Rift. The crack followed the path of an existing rift-related fracture. Rain had acted as a trigger at the surface, removing support from material that concealed a much older weakness. The underlying structure had been developing through tectonic forces for millions of years. When the covering soil gave way, a process normally perceived through maps, measurements, and distant satellite observations became visible from the roadside. That distinction matters. A fracture appearing after rainfall can look like a new wound created by the storm itself, while the geology may have been preparing the ground for far longer. The event, therefore, became a rare meeting between everyday weather and deep planetary movement. A season of rain exposed a boundary whose origins reach far below farms, roads, and villages. Images of the opening spread rapidly around the world. They showed raw earth crossing cultivated land and pavement with no conventional construction project or surface machinery responsible for the divide. The scene offered an unusually direct glimpse of a continent undergoing gradual deformation. The ground beneath East Africa could appear stable for generations, then reveal movement through a fracture that had been developing beyond ordinary human perception. The Kenya event also belongs beside the fissure that opened in Afar 13 years earlier. Both occurred along the same broader system of continental stretching, where faults, magma, and changing stresses reshape the crust. Each event represents a small movement within a geological process that began roughly 35 million years ago. The visible opening may last for a moment in human history, while the separation itself unfolds across millions of years. For geologists, such episodes provide something precious, direct observations of a living rift. Measurements from the surface can be compared with seismic signals and satellite records, allowing scientists to connect what happens underfoot with structures extending through the crust. Kenya's fracture became more than a damaged road. It became another visible mark of a continent gradually changing its shape. The episode also showed why the surface cannot reveal the full age of a fracture. A crack may appear overnight, while the forces preparing it have worked for generations. Sudden ground movement can therefore express a process already underway deep within the continent. Across the Afar region, the Danakil, and the rift valleys of Kenya and Ethiopia, the continent carries a geological change that can be measured deep below the surface. Continental crust usually extends about 40 kilometers, which is about 25 miles, to 56 kilometers, that is nearly 35 miles, beneath stable regions. This thick foundation gives continents their familiar elevation and strength. In the central Afar region, geophysical measurements reveal a very different structure. In some places, the crust has thinned to roughly 19 kilometers, which is about 12 miles. In the most advanced zones, estimates fall toward 6 to 10 kilometers, that is nearly 4 to 6 miles. Such dimensions bring the base of the continent remarkably close to the composition and density normally associated with oceanic crust. Thinning changes the landscape above it. As the crust loses thickness, the surface can subside, helping explain why parts of the Danakil lie more than 120 meters, which is about 400 feet, below sea level. The mantle also rises closer to the surface, allowing heat to travel through less rock. That steeper thermal path helps produce the intense volcanic and geothermal activity scattered through the rift. The shape of the land records another consequence. Stretching crust breaks along long, roughly parallel faults. Blocks caught between those fractures can sink, creating structures called grabens, while neighboring blocks rise into horsts. Together, these raised and lowered sections form the repeating pattern of valleys and highlands that marks the rift from Ethiopia toward Mozambique. The landscape therefore carries the geometry of the forces acting within it. In parts of Kenya, the floor of the rift lies nearly 1,800 meters, which is about 5,900 feet below the surrounding highlands. That difference creates immense vertical relief across the landscape. Similar fault-bounded valleys appear again and again along the rift, each shaped by the gradual separation of the continental crust. Scientists can trace this hidden architecture using seismic tomography. Earthquake waves travel through rock at different speeds depending on its composition, temperature, and thickness. By measuring those changes as waves pass through the planet, researchers can build images of structures that cannot be seen from the surface. The Afar region has become one of the clearest natural laboratories for observing continental thinning while it is still underway. That thinning also helps explain why volcanic centers gather along particular sections of the rift. Magma can exploit faults as pathways upward, while heat from deeper rock warms groundwater, moving through fractured crust. Each process leaves a different signature, yet all arise from the same reduction in thickness. As the mantle approaches the surface, the interior of Earth can influence the landscape more directly. In Afar, the transition can be followed from elevated continental blocks to deep basins, then toward zones where oceanic conditions are beginning to emerge. The deepest part of the story lies in what happens when thinning continues far enough. Oceanic crust is generally denser and compositionally different from ordinary continental crust, and portions of the Afar already show characteristics approaching that state. The boundary between continent and ocean is therefore becoming less distinct at the northern end of the rift. What appears above ground as valleys, escarpments, volcanoes, and salt flats is connected to a deeper transformation where the foundation itself is being stretched toward a new geological identity. For thousands of miles, the rift carries a chain of volcanic centers from Ethiopia toward Mozambique. Across roughly 6,400 kilometers, which is about 4,000 miles, the crust is being stretched, heated, and fractured, giving magma more opportunities to rise. The volcanoes are scattered, yet their distribution follows a larger pattern. Each one marks a place where heat from Earth's interior has found a pathway through thinning continental rock. In the western branch, Mount Nyiragongo rises above the Democratic Republic of Congo near the city of Goma. Its summit crater holds a lava lake that has appeared and disappeared through cycles of activity, and its unusually fluid lava can travel at speeds approaching 97 kilometers per hour, which is about 60 miles per hour. In January 2021, an eruption sent lava toward Goma, prompting the evacuation of roughly 400,000 people. The event showed how rapidly a deep geological process can enter the scale of everyday human life. Far to the east, Tanzania contains one of the strangest volcanic systems on Earth. Ol Doinyo Lengai is the only known active volcano that erupts carbonatite lava. This unusual molten material contains very little silica and can emerge at temperatures near 510 degrees Celsius or 950 degrees Fahrenheit. That is far cooler than typical basaltic lava. When carbonatite lava hardens, it can appear pale or almost white, leaving the crater with a surface unlike the familiar black rock associated with most volcanoes. Kenya holds another expression of this volcanic inheritance at Menengai. The caldera stretches about 9 kilometers, which is about 5.6 miles, across and formed through a major collapse roughly 8,000 years ago. Heat remains active below the depression, and geothermal wells now draw that underground energy toward the surface, turning volcanic heat into electricity. Mount Kilimanjaro presents a different stage of the same regional story. Its summit reaches about 5,895 meters, which is about 19,341 feet, above sea level. 3 volcanic cones form its distinctive profile. The most recent major summit activity occurred roughly 200,000 years ago, and the mountain is considered dormant rather than extinct. Its presence records a region where volcanism has shaped not only valleys and lava fields, but one of Africa's defining landscapes. The volcanic history of Ethiopia reaches farther back, around 30 million years ago. Enormous eruptions spread basalt across more than 600,000 square kilometers, which is about 230,000 square miles, building much of the Ethiopian highlands. These flood basalts appeared around the same broad period when rifting began near Afar, linking surface eruptions with deeper changes in the mantle beneath the region. Layer after layer of lava accumulated, turning immense areas into a volcanic plateau. Seen together, these volcanoes form a connected geological family. Some hold molten rock at their summits, some release unusual lava, and others preserve the broad scars of ancient eruptions. Their differences reflect local conditions within one larger system. Wherever stretched crust becomes thin enough, heat and magma can approach the surface, giving the rift a visible expression along its long path through eastern Africa. The pattern is persistent across the rift, with volcanic centers appearing where fractures, heat, and rising magma meet within the thinning crust. The ground around Hadar has preserved a meeting between geology and human history. In November 1974, paleoanthropologist Donald Johanson and his team found fragments of a small skeleton in an eroded hillside within the Afar Depression. The remains belonged to a female who lived 3.2 million years ago. She stood only about 1.1 meters, which is about 3.6 feet, with a brain roughly one-third the size of a modern human brain. At the campsite that evening, a Beatles song was playing, and the name Lucy was chosen for the fossil. Her importance rested in the bones that remained. The shape of her pelvis, the angle of her thigh bones, and the structure of her lower limbs showed that she could walk upright on two legs. Her brain remained comparatively small, closer in scale to that of an ape than a modern human. That combination altered the story scientists had been building about our origins. Upright walking had appeared long before the great expansion of the human brain. Movement across two legs was therefore an early chapter, while larger brains came much later. The Afar preserved another piece decades later. In 1994, researchers working farther north recovered a skeleton about 4.4 million years old. It was given the name Ardi from the species Ardipithecus ramidus, and its anatomy also contained evidence consistent with upright walking. The discovery pushed bipedal movement deeper into the past, into a period when our ancestors still lived among a mixture of woodland and more open environments. Farther south, Tanzania offers an even more direct trace. In 1978, a team led by Mary Leakey uncovered a trail of footprints at Laetoli, preserved in volcanic ash. The impressions were about 3.6 million years old, and their sequence recorded individuals walking upright across the surface of the ancient landscape. Unlike isolated bones, footprints preserve movement itself. Each step became a brief record of how an early human relative carried its body through the world. The landscape surrounding these discoveries matters because the rift does more than fracture rock. Its uplift can alter elevation, rainfall, drainage, and the distribution of vegetation. Along portions of the eastern branch, rising terrain contributed to regional drying, while forests gave way to more open grasslands. Those changing habitats created new pressures for animals that had once moved through trees. Walking efficiently on two legs could offer advantages across open ground, allowing hands to remain available for carrying food, infants, or other objects. This idea became known as the East African Rift hypothesis, developed through decades of research by many scientists. It does not reduce human evolution to a single cause, because climate, ecology, anatomy, and chance all interacted. The rift formed one part of that changing setting, shaping the landscapes where early hominins lived and where their remains were later preserved. Lucy, Artie, and the Laetoli footprints therefore belong to the same geological story that is still unfolding across eastern Africa. Their fossils were protected by sediments, volcanic ash, and changing terrain within the rift system. The same forces that opened valleys and raised highlands also created the landscapes in which our ancestors adapted. Deep in the record of those rocks lies a remarkable continuity. The continent is being reshaped beneath our feet, and within that reshaping, one branch of life learned to walk upright. The shape of East Africa's wildlife map is partly a story written by moving rock. As the rift lifted sections of the continent, it changed the direction of rivers, raised new barriers, and created basins where water could gather. A landscape once dominated by westward drainage toward the Proto-Congo Basin was gradually reorganized. Some rivers found routes toward the Nile, while others were redirected southward toward the Zambezi. The animals followed the water, and generations of plants followed the altered soils. Lake Victoria carries one of the clearest signatures of this transformation, covering about 68,800 square kilometers, which is about 26,560 square miles. It lies between the eastern and western branches of the rift rather than inside either branch. Its shallow basin developed through a combination of uplift, faulting, and changing drainage, with major portions of the modern lake taking shape within the last few 100,000 years. As surrounding land rose, drainage patterns changed and water accumulated in the depression. From its northern outlet, the White Nile begins a journey that connects this inland basin with the Mediterranean world. Farther south, the Serengeti reveals another consequence of the same geological architecture. Each year, roughly 1.5 million wildebeest, 400,000 zebras, and 300,000 Thompson's gazelles move across the plains in search of fresh grass and water. Their route passes through terrain influenced by volcanic activity along the rift. Ash and lava weathered into mineral-rich soils, supporting grasses that can sustain enormous herds. The migration is therefore partly a biological response to geology, repeated season after season across a landscape whose foundations were shaped deep underground. Near the Serengeti stands the Ngorongoro crater, a volcanic caldera about 16 kilometers wide, which is about 10 miles, and roughly 600 meters deep, which is about 2,000 feet. Its walls enclose grasslands, forests, wetlands, and a permanent water supply, creating an unusually compact habitat for large mammals. Around 25,000 large animals live within the crater and its surrounding ecosystem. Lions, elephants, buffalo, rhinoceroses, and other species occupy different parts of the enclosed landscape, their distribution shaped by elevation, water, vegetation, and the crater's volcanic soils. The western branch carries this geological influence into forests rather than open plains. Across the Albertine Rift, steep mountains, deep valleys, volcanic slopes, and isolated habitats produce extraordinary biological variety. Mountain gorillas survive within highland forests along the borderlands of several countries. Populations separated by ridges and valleys can remain isolated for long periods, allowing distinctive forms to emerge. Here, the rift acts as both a pathway and a wall, depending on the species and the landscape. That dual role reaches across the entire region. A new escarpment can divide populations that once mingled freely, while a river valley can provide a corridor between habitats. Over millions of years, Repeated changes in elevation, water, vegetation, and climate create opportunities for populations to diverge. Geological movement, therefore, becomes biological history. The same forces that rearranged rivers and raised mountains also produced the boundaries within which new species could develop, leaving East Africa with a living record of continental change. In this way, the rift does more than divide the ground. It sorts landscapes into distinct worlds, each with its own water, vegetation, altitude, and communities of life, allowing biodiversity to accumulate where geological change keeps creating new boundaries. For most of Earth's history, a continent could begin to split without leaving any record of the moment itself. The evidence arrived much later as altered rocks, volcanic layers, broken landscapes, and oceans where land had once stood. The East African Rift offers something profoundly different. For the first time, instruments can follow continental separation while it is happening, measuring movements too small for the human eye, yet large enough to reshape a continent across geological time. Across the rift, networks of global positioning system receivers measure the changing positions of the ground with extraordinary precision. Some stations can detect motion of only a few millimeters each year. In the southern reaches, the Somalian plate is separating from the Nubian plate by roughly 2.5 to 7 millimeters per year, which is about 1/10 to 3/10 of an inch. Near the Afar region, the rate can approach 20 millimeters per year, which is about 8/10 of an inch. These numbers seem almost delicate, yet their persistence gives scientists a direct measurement of continental movement. The value of these instruments became especially clear during the Afar crisis of 2005. A large body of magma forced its way through the crust, opening fractures across a long section of the rift. Surface stations recorded the ground moving apart as the intrusion developed, while changes in elevation and position traced the path of the molten rock below. In some areas, the separation accumulated to roughly 8 meters, which is about 26 feet, within only a few weeks. A process once imagined through ancient landscapes could now be followed through measurements, arriving almost as the Earth itself moved. Satellites added another layer of vision. Interferometric synthetic aperture radar compares radar images collected at different times, allowing scientists to detect extremely small changes in the shape and position of the ground across enormous regions. A single image can reveal deformation spread over many kilometers, which is about many miles, while repeated observations can show how faults and magma intrusions develop between widely separated monitoring stations. Features that might escape notice from the surface become patterns when viewed from above. The resulting picture is more intricate than a single fracture advancing through the continent. The rift is a connected system of faults, volcanic centers, and stretched crust, with neighboring sections opening at different rates. Some episodes unfold gradually, while others accelerate when magma enters the crust. The 2005 Afar event helped establish that continental rifting can proceed through pulses, with periods of rapid deformation separated by longer intervals of slower movement. These observations also have a practical purpose. Measurements from satellites and ground stations contribute to volcanic and earthquake monitoring across East Africa, helping scientists recognize changes that may signal renewed activity. The same instruments that record a continent changing its shape can therefore serve communities living across the rift. Human technology has finally given this geological transformation a witness, turning movements measured in fractions of an inch into a record of Africa becoming something new. Each station becomes one small point in a continental scale observation system, while satellites connect those points across deserts, mountains, valleys, and volcanic fields. The changing numbers form a living chronicle of a landscape still in motion, recorded day after day from above and below. Heat rising from the crust has become more than a geological signature across East Africa. In some places, it has become electricity. The same stretching that thins the continental crust also allows hot rock and magma to approach the surface, creating reservoirs of steam and heated water that can be tapped for power. Along the rift, the boundary between geology and daily life becomes unusually close. Geothermal energy is produced by drawing heat from inside Earth. Wells reach underground reservoirs where water has been warmed by the surrounding rocks, sometimes to temperatures high enough to produce steam. That steam can turn turbines and generate electricity. The rift is especially suited to this process because its crust is fractured, its heat flow is high, and molten material remains relatively close to the surface. In some areas, the hottest zones lie less than 3 kilometers, that is nearly 2 miles, below ground. Kenya has made the most extensive use of this resource. Around the Olkaria geothermal complex, in the volcanic landscape of Hell's Gate, wells descend into a network of hot rock and circulating water. Steam brought upward through these wells powers turbines, turning deep geological heat into electricity that can travel through the national grid. In recent years, geothermal sources have provided more than 40% of Kenya's electricity, making the rift a major part of the country's energy system. The setting itself carries an unusual harmony. Hell's Gate National Park contains cliffs, volcanic formations, hot springs, and geothermal features alongside wildlife and working energy infrastructure. The same underground heat that shapes the landscape also supports a modern power industry. Water moves downward through fractures, gathers heat, rises again through pressure and permeability, and can be captured before returning to the underground system. Kenya is only one part of a much larger possibility. Ethiopia, Tanzania, Djibouti, and Rwanda are developing geothermal resources associated with the rift, each working with different combinations of volcanic activity, groundwater, and accessible heat. Estimates from the United Nations Environment Program have suggested that the region holds substantial geothermal potential, enough to contribute far more electricity than it currently produces. The resource is renewable on human timescales when reservoirs are carefully managed because the heat source is continually replenished from Earth's interior. There is a particular grace in this exchange. A continent being pulled apart can also offer a source of power for communities living across the same changing ground. The fractures that allow magma to rise can also allow water to circulate deep into the crust. The heat that escapes through volcanic landscapes can become steam, and the steam can become light in homes, energy for hospitals, and power for growing cities. Geology rarely arrives as a single story. The rift carries earthquakes, volcanoes, lakes, fertile soils, and deep biological history, yet it also carries heat that people can use. For East Africa, the opening of the continent has created an energy landscape where the Earth's internal warmth is no longer only evidence of change. It has become part of the region's present, drawn upward from the same deep engine that continues to reshape the land. At Olkaria, this transformation is visible. Boreholes connect an underground reservoir to pipes, turbines, and transmission lines, creating a chain that begins with heat locked in rock and ends with electricity used far beyond the volcanic fields. The landscape becomes a meeting place between deep earth and human infrastructure. A map of Africa, drawn from ordinary coastlines, suggests a future divided into two broad pieces. Modern measurements tell a more intricate story. Across the East African rift, the ground is responding to several moving fragments, each carrying its own direction and rhythm. The continent is becoming less like a sheet being torn in two and more like a mosaic whose pieces are beginning to find their own paths. The largest plates still provide the broad framework. The Nubian plate occupies most of Africa, while the Somalian plate is gradually moving away toward the east. Between them, however, global positioning system measurements have revealed smaller blocks that behave as independent units. These microplates are large enough to influence the geometry of faults and rift valleys, yet small enough for their movements to be masked within the broader motion of the continent. Near Lake Victoria lies the Victoria Plate, a fragment whose movement differs from the surrounding Nubian and Somalian plates. Its position between the eastern and western branches gives it a special geological role. As it shifts, the faults around it adjust, helping produce differences in direction and opening rate between the two branches. The lake therefore rests above a piece of crust, participating in the larger rearrangement, even though the changes beneath it unfold too gradually for ordinary perception. Farther south, the Rovuma Plate adds another layer of complexity. Recognition of its independent motion emerged from measurements collected during recent decades, when satellite positioning became precise enough to distinguish smaller movements from the broader separation of the major plates. The Rovuma Plate occupies parts of southern Tanzania and northern Mozambique, near a region where the eastern and western branches draw closer together. Its movement does not fit neatly into a simple two-plate picture, giving geologists another moving piece to account for. Beyond the continent, the Luwandle Plate occupies part of the southwestern Indian Ocean and interacts with the southern end of the rift system. Its motion connects the continental story with deformation beneath the ocean, where the boundaries between crustal fragments become increasingly difficult to draw as clean lines. The developing system reaches across thousands of kilometers, which is about thousands of miles, linking inland valleys with the floor of the Indian Ocean. This complexity changes the way the future can be imagined. A new ocean may eventually occupy the broad region of separation, yet the exact arrangement of its shores cannot be predicted, as though two neat halves were moving apart. Several fragments may rotate, shift, or accommodate motion along different fault zones. Some boundaries may become clearer, while others may disappear as new ones form. Every new measurement adds another piece. A global positioning system, station, records a fraction of movement that, repeated across years, reveals a direction. Satellite observations connect those points across distances too large for any single field team to follow. The geological map, therefore, remains a living document, refined whenever the crust offers another measurable adjustment. Africa's future is being written through these small motions. Each microplate carries a portion of the continent toward a configuration that has no exact modern equivalent. The final geography will emerge from countless movements occurring together, each one modest on a human scale, yet collectively capable of redrawing an entire continent. Their boundaries are therefore provisional, shaped by evidence that continues to accumulate across the moving landscape. A continent can begin to separate without ever reaching the open sea. That possibility places a gentle uncertainty over the story of the East African rift. The fractures, volcanoes, lakes, and moving plates all show a continent being stretched, yet stretching alone does not guarantee that an ocean will eventually occupy the gap. Some rifts spend millions of years opening, then lose the energy that sustained them and remain as scars within otherwise solid land. Geologists have a name for these unfinished attempts, an olicogen. It is a failed rift, later buried beneath layers of sediment whose presence can still be traced through unusual gravity and magnetic patterns. The Earth preserves these abandoned experiments with extraordinary patience. Their former valleys may disappear beneath forests, farms, cities, and newer rocks, while instruments reveal the shape of fractures that stopped moving long ago. North America's mid-continent rift offers a striking example. About 1.1 billion years old, it once carried enormous volcanic outpourings through the interior of the continent. For roughly 20 million years, the crust opened and magma rose through the developing fracture system. Then the process stopped. Today, the old rift extends from Kansas toward Lake Superior and through Michigan, concealed beneath the landscape and recognized largely through geophysical measurements rather than an obvious surface boundary. For a continental rift to become a true ocean basin, several conditions have to persist together. Heat from the mantle must continue weakening and thinning the crust. Plate driving forces must keep pulling the land apart. Eventually, seawater must gain access to the developing depression. Water changes the physical balance of the system and marks the transition from an inland continental rift toward a spreading oceanic environment. Without that marine flooding, a widening valley can remain isolated from the world's oceans and eventually cease opening. This possibility matters most along the western branch of the East African Rift. Its opening has generally progressed more slowly than the eastern branch, while magma supply and crustal thinning appear less advanced in several areas. The difference does not mean that the western branch must stop. It means that its future carries more uncertainty than a simple picture of two equal continental halves drifting apart would suggest. Should that branch eventually stall, the geography would be very different. The Somalian plate could separate as a smaller fragment containing the Horn of Africa and portions of coastal East Africa, while the Western Rift remained as a geological scar. Countries farther inland could retain their continental setting, with no new ocean shore arriving along the route imagined by a complete rupture. At Afar, the situation is more advanced. The crust has become exceptionally thin, and portions of the system have already developed characteristics associated with oceanic crust. That makes the northern end a strong candidate for eventual marine opening. Still, the entire rift stretches for about 6,400 kilometers, which is about 4,000 miles, and its branches do not behave as one uniform machine. The most honest picture is therefore unfinished. Africa is separating in measurable ways, yet geology offers no promise that every fracture will reach the same destination. Some portions may continue opening, others may slow, and one branch could preserve the memory of an ocean that never arrived. Picture Africa several million years from now, with the present borders erased by changes too gradual for any single generation to notice. The most likely geological path begins with the rift continuing its patient separation. Faults extend, crust becomes thinner, volcanic centers remain active, and some of the great rift basins deepen as their floors settle. The continent would still look familiar from a distance, yet its internal architecture would be steadily rearranging itself. At the northern end, the geography changes first. The Afar Depression already lies low enough for seawater to enter once a marine connection develops from the Red Sea and Gulf of Aden. Geological studies indicate that the transition from continental rifting toward a new ocean can occur on a timescale of roughly 10 million years, although the exact sequence remains uncertain. As the land sinks and the connection advances, seawater could spread into the Danakil Depression, turning parts of today's desert into a shallow marine basin. The change would begin as an inland sea, surrounded by volcanic ridges and newly forming coastlines. Farther south, continued extension would allow the marine basin to lengthen through the rift system. New oceanic crust would form where molten rock rises into the widening gap and cools, gradually replacing stretched continental crust. The Red Sea offers a useful, natural comparison because it already records an earlier stage of this same transition. Given enough time, the new waterway could develop its own spreading center, with fresh seafloor forming along its middle as the separated land masses drift farther apart. The Horn of Africa would occupy the eastern side of this new basin. Somalia, Djibouti, and portions of eastern Ethiopia and Kenya could become part of a large continental fragment, separated from the Nubian portion of Africa by the widening sea. Existing Indian Ocean coastlines would acquire a very different setting. Kenya, Tanzania, and Mozambique would face waters connected to the new basin, while their familiar relationship with the open Indian Ocean would be reshaped by the changing continental boundary. The consequences would reach far inland. Uganda, Rwanda, Burundi, Zambia, and the Democratic Republic of Congo are presently landlocked, yet a completed marine connection could eventually place some of these regions much closer to, or directly beside, a new coastline. Ports could appear along shores that today are grassland or forest. Fishing grounds could develop where dry valleys once crossed the continent, while submarine communication cables and offshore industries could follow the new margins. Such a map would also redraw political and economic relationships. Coastlines influence trade routes, settlement patterns, access to resources, and the location of major cities. A country that is inland today could become maritime territory after millions of years of tectonic change, while a present coastal nation could find its surrounding waters transformed into part of a younger ocean. The full rift spans about 6,400 kilometers, which is about 4,000 miles. The completed basin would eventually acquire the character of a true oceanic system. A central spreading ridge could generate new crust continuously, much as ridges do elsewhere across the planet. The African map would then show a continent divided by an ocean born from its own interior, with coastlines marking the place where solid land once stretched across an unbroken landscape. The floor of the Danakil Depression carries a record that can be read in layers, each one preserving a different chapter in the changing relationship between land and sea. What appears today as a harsh salt plain was shaped through repeated episodes of flooding, evaporation, uplift, and drying. The basin has acted like a natural ledger, collecting minerals whenever water entered and leaving them behind when the heat of the region returned the water to the atmosphere. In places, the accumulated salt beneath the depression may reach about 4.8 kilometers in thickness, which is about 3 miles. Within that immense sequence, individual layers preserve changes in the chemistry of the waters that once occupied the basin. As seawater evaporates inside an enclosed basin, dissolved minerals crystallize in a recognizable order. Calcium carbonate forms first, followed by gypsum, and eventually halite, the mineral commonly known as table salt. The sequence provides geologists with clues about where the water came from and what conditions existed as evaporation progressed. When evaporation continues, the basin can become chemically concentrated enough for unusual salts to appear, preserving a changing record of the waters that once occupied the depression. Volcanic ash offers another kind of clock, Thin ash beds can become trapped between salt deposits when eruptions spread material across the basin. By dating minerals within those ash layers, researchers can establish ages for the surrounding deposits and reconstruct the timing of ancient flooding events. The resulting record reaches beyond a single episode, allowing the history of changing water levels, volcanic activity, uplift, and erosion to be compared across long stretches of geological time. The rhythm preserved in the basin reflects a landscape that has never remained fixed. As surrounding highlands rise and erosion lowers them again, drainage pathways change, and the possibility of marine or lake flooding changes with them. Climate also alters the balance. A wetter interval can allow water to persist longer, while stronger evaporation leaves thicker mineral deposits behind. The desert visible today, therefore, represents one phase within a much longer sequence of environmental change. The boundaries between these deposits can be as informative as the deposits themselves. A sudden change from one mineral sequence to another may mark a shift in water depth, climate, drainage, or volcanic influence, giving the archive a layered sense of cause and effect. Heat adds another layer to this archive. Magma beneath the rift warms groundwater and circulating fluids, sending mineral-rich water through fractures and sediment before it reaches the surface. At the Dallo hydrothermal field, these fluids emerge among acidic pools, sulfur deposits, and mineral crusts colored by chemical reactions. The extraordinary shades are physical expressions of minerals separating from hot fluids as temperature, acidity, and chemistry change across very small distances. For the Afar people, salt has also been part of a living human history. For centuries, workers have cut slabs from the Danakil salt flats and loaded them onto camel caravans bound for markets in the Ethiopian highlands. The journey connects the mineral floor to settlements far above the depression, where salt became an important trade commodity and, in earlier periods, could function as a form of money. The same substance that records vanished waters has therefore carried geological history into everyday human exchange, passing from the floor of the rift into hands, markets, homes, and distant highland communities for generations across the region. Both emerge from the same geological source. The East African Rift is written into the lives of people who inhabit it. Across its length, the same geological forces that raise fertile ground and sustain water systems can also fracture roads, awaken volcanoes, and shake cities. More than 150 million people live within the broader rift zone, making this one of the rare places where continental transformation is both a scientific process and an everyday reality. In 2021, Mount Nyiragongo demonstrated how quickly that reality can change. Lava moved toward Goma, a city of roughly 670,000 people, after an eruption opened fractures on the volcano's slopes. Around 400,000 residents fled within hours. 32 people died, more than 3,500 homes were destroyed, and direct damage reached an estimated $50 million. The eruption also left the city with a lingering geological unease. 2 weeks later, cracks began appearing in the ground as magma continued moving through the region. Lake Kivu carries another kind of hazard. Around 2 million people live along its shores, beside deep water containing large quantities of dissolved volcanic gases. These gases are held under pressure within the lake, and a sudden disturbance could release them into the atmosphere. The possibility is known as a limnic eruption, a rare event in which dissolved gases escape rapidly from deep water. Lake Nyos, in Cameroon, provided a devastating example in 1986, when a gas release killed about 1,000 700 people during a single night. Kivu is vastly larger, making its geological chemistry an important concern for communities around the lake. Earthquakes form a more familiar part of life along the rift. Nairobi, Kampala, Dar es Salaam, and Addis Ababa have all experienced seismic activity associated with the broader tectonic setting. Millions of people live in these expanding urban centers, where buildings, roads, bridges, and utilities were often designed around assumptions that may not fully reflect a moving crust. The danger grows where dense development meets weak ground, steep slopes, or poorly reinforced structures. Across the rift floor, infrastructure occupies some of the land undergoing the greatest geological change. Roads, railways, pipelines, farms, and settlements cross faulted ground that can rise, sink, or crack as the plates continue adjusting. In Kenya, the Nairobi to Narok Road suffered a major collapse in 2018 after ground movement opened a deep rupture across the route. Such failures can feel sudden to the people affected, even when the geological forces producing them have been accumulating for generations. There is another side to this relationship, written into the soil itself. Volcanic ash supplies minerals that weather into exceptionally fertile ground, supporting intensive agriculture across parts of East Africa. Crops grow in landscapes shaped by eruptions that occurred thousands or millions of years earlier. The benefits arrive gradually through soil formation and water retention, while the hazards can appear in a single night. For communities along the rift, geology therefore has no distant boundary. It is present in the ground beneath homes, in the roads crossing valleys, in the lakes beside growing cities, and in the fields that feed families. The continent is changing at a pace too slow for human eyes to follow, yet its effects can still enter an ordinary day. Africa's separation belongs to a rhythm far older than the landscape taking shape around the rift. Continents gather, break apart, drift across the planet, and gather again. The process unfolds so slowly that a human lifetime occupies almost no space within it, yet the forces responsible are active beneath every ocean and mountain range. At the heart of this rhythm is the supercontinent cycle. Earth's mantle is constantly transferring heat through movement deep below the crust. That motion helps fracture continents and open new oceans, while older oceanic crust gradually cools, becomes denser, and sinks back into the mantle at subduction zones. As ocean floor disappears, the continents carried above it are drawn toward other landmasses. A boundary that once widened can eventually become the place where continents meet. The ocean created by Africa's separation would therefore have a limited geological lifetime. After its birth, its seafloor would begin cooling and gaining density. Given enough time, portions of that oceanic crust could descend beneath neighboring plates, feeding the same deep circulation that helped create the basin. The new sea would widen, mature, and eventually begin closing. Shorelines that once moved apart would slowly reverse their journey, with continents converging across an ocean that had seemed permanent to every civilization living beside it. Geologists use computer models to explore what that distant world might resemble. Several possibilities have emerged for roughly 200 to 250 million years from now. One model, known as Amasia, places much of the future supercontinent around the Arctic region. Another, called Pangea Ultima, imagines the Atlantic closing and the continents assembling around the resulting landmass. A third possibility, Novopangea, follows a different sequence of ocean opening and closure. None can be treated as a finished map. The positions of continents depend on countless interactions that cannot yet be predicted across such immense spans of time. Where continents collide, the crust can buckle into mountain systems. India provides a glimpse of this process. After separating from Gondwana, the Indian landmass traveled northward for roughly 100 million years before colliding with Eurasia around 50 million years ago. That encounter helped raise the Himalayas, whose peaks reach elevations comparable to the greatest mountain ranges produced by continental collision. A future gathering of continents could create another chain of similar scale, although its exact position and form would depend on the arrangement of the land masses at that distant moment. The fragment, now moving away from Africa, would take part in this larger cycle. The Somalian plate could continue drifting eastward for tens of millions of years, crossing an ocean that has yet to exist. Much later, that same piece of continental crust could become joined to lands now separated from it by thousands of miles of water. Coastlines, mountain ranges, inland seas, and deserts would all belong to a geography with no resemblance to the present one. Seen across these immense intervals, continental breakup is only one movement within a much larger planetary rhythm. Oceans are born, mature, and disappear. Continents separate, wander, and converge. The surface changes its arrangement while the deeper Earth continues, transferring heat and reshaping the crust. Africa's present fracture is therefore one measured pulse in a cycle that has been turning for hundreds of millions of years, long before any human observer could name a continent. Earth's surface can seem permanent when viewed across a human lifetime, yet its shape is governed by a deeper clock. That clock is powered by heat left from the planet's formation about 4.54 billion years ago, together with heat still being produced inside it. Every mountain, basin, volcano, and moving plate belongs to this long release of internal energy. Part of Earth's heat comes from its earliest assembly. As rock and metal gathered under gravity, their motion and compression transformed enormous amounts of gravitational energy into heat. Some of that warmth remains stored deep within the planet. Another source continues today through radioactive decay. Elements such as uranium, thorium, and potassium gradually break down inside the mantle and crust, releasing small amounts of energy with each decay. Across billions of years, those tiny contributions become a sustained source of planetary heat. That energy keeps the mantle moving. Solid rock deep inside Earth can flow over geological timescales, carrying heat upward while cooler material sinks. The movement is extraordinarily slow, generally measured in a few centimeters per year, which is about an inch per year, yet its persistence gives it immense influence. A motion too gradual to notice directly can shift continents, open oceans, build mountain belts, and reshape coastlines when allowed to continue for millions of years. The rift in East Africa belongs to this same circulation. Heat rising through the mantle helps weaken and thin the crust, while the movement of tectonic plates responds to forces distributed across the planet. The fractures, volcanic systems, and changing elevations seen across the region are surface expressions of energy traveling through a much deeper Earth. What appears as movement of land is connected to a process unfolding far below human reach. Mars offers a contrasting chapter. Being smaller, the planet lost internal heat more efficiently, and its interior eventually became less capable of sustaining the kind of global plate recycling found on Earth. Its enormous Valles Marineris stretches for roughly 4,000 kilometers, which is about 2,500 miles, and reaches depths of about 6 kilometers, that is nearly 4 miles. Scientists have proposed that this immense canyon system formed through ancient tectonic and volcanic processes, although it is not regarded as a direct counterpart of a terrestrial ocean forming rift. Earth's continued activity makes the contrast meaningful. Its interior still contains enough energy to move plates, feed volcanoes, create new crust, and maintain the geological circulation that continually renews the surface. The heat is not an isolated reservoir waiting beneath the continents. It is part of a planetary system in motion, transferring energy through rock on timescales far beyond ordinary experience. That system will eventually change. As Earth loses heat across immense spans of time, mantle convection is expected to weaken. Plate movements may become slower, volcanic activity may decline, and the mechanisms that recycle crust could gradually fade. The planet would still remain a world of rock, water, atmosphere, and mountains, yet its surface would become less dynamically renewed. For now, the moving ground of East Africa marks a different moment in Earth's history. The planet is still releasing the energy inherited from its birth, still creating fractures where continents pull apart, and still turning internal heat into changes that can be traced across the surface. The rift is therefore more than a boundary between moving plates. It is a visible measure of a deeper clock, one whose hands have been turning since the world itself began. A journey along the eastern side of Africa can feel like moving through a living archive. From the Afar Depression in Ethiopia to the volcanic plains of Tanzania and Kenya, layers of sediment and ash preserve traces of creatures that walked here millions of years ago. The geological setting that shaped these landscapes also created places where the human past could be buried, preserved, and eventually uncovered. In the Afar Depression, two of the most famous early human relatives emerged from the same broad geological region. Ardi, a specimen of Ardipithecus ramidus, lived about 4.4 million years ago and was discovered near the Awash River in Ethiopia in 1994. Lucy, an Australopithecus afarensis, who lived about 3.2 million years ago, was found at Hadar in 1974. Their bones belong to very different moments in human evolution, yet both were preserved within sediments deposited in a landscape continually reshaped by tectonic movement, volcanic activity, rivers, and changing lakes. Further south, at Laetoli in Tanzania, another kind of evidence survived. In 1978, researchers working with Mary Leakey uncovered footprints preserved in volcanic ash. Around 3.6 million years ago, at least two early hominins crossed the soft surface after an eruption had spread ash across the ground. Their impressions captured the sequence of individual steps, preserving a physical record of movement itself. The footprints remain among the oldest direct evidence of a human ancestor walking across a landscape. Olduvai Gorge adds another layer to this record. An ancient river carved through successive deposits in the rift region, exposing sediments that contain fossils, animal remains, and stone tools. Louis Leakey, Mary Leakey, and later researchers recovered numerous hominin specimens from layers spanning roughly 2.1 million years. Because the deposits accumulated in recognizable sequences, they provide an unusually continuous view of biological and technological change across a long interval of human evolution. Geology also helped shape the environments in which these early populations lived. Uplift along the eastern branch of the rift, altered elevations, and atmospheric circulation, influencing rainfall patterns across surrounding regions. In some areas, forests gave way to more open habitats. Such environmental changes created shifting pressures on animals living along the rift margins. Upright walking, efficient movement across open ground, flexible diets, cooperation, and increasingly sophisticated tool use all developed within a changing ecological setting. Although no single geological event can be assigned as the sole cause of human evolution, the archaeological record follows this geography. At Lomekwi in northern Kenya, researchers discovered stone tools dated to about 3.3 million years ago. These objects predate the earliest members of our genus and show that toolmaking began before Homo sapiens appeared. Across later ages, stoneworking became increasingly elaborate, eventually producing technologies far removed from their earliest forms. The connection reaches into the human body itself, although it is more complex than a single environmental explanation. Our upright posture, long lower limbs, grasping hands, and forward facing eyes emerged through many stages of evolution. The rift landscapes formed part of that history by repeatedly changing climate, terrain, water availability, and food resources. Along this geological corridor, the rocks preserve fossils, footprints, tools, and sediments that together record a remarkable passage from early hominins to our own species. The future map of Africa carries a cost that is easy to miss when attention rests on new seas and coastlines. Every landscape reshaped by tectonic movement also loses something that took immense spans of time to develop. Along the rift, that loss begins with water, where isolated lakes have become evolutionary worlds of their own. Tanganyika, Malawi, Kivu, Turkana, Albert, and Edward hold communities found nowhere else. Their separation from other waters allowed fish, mollusks, crustaceans, and countless smaller organisms to follow different evolutionary paths. Lake Malawi is especially rich, with estimates of roughly 800 to 1,000 cichlid species, many restricted to particular parts of the lake. Their diversity accumulated through repeated isolation, adaptation, and competition across millions of years. When seawater eventually reaches these basins, their chemistry will change profoundly. Freshwater specialists cannot simply move into a marine environment, and entire lineages could disappear as salt replaces the conditions that allowed them to flourish. Some species might retreat into surviving freshwater pockets for a time, yet isolation itself would become harder to maintain as waterways merge, salinity spreads, and the boundaries between separate lake ecosystems disappear. The Serengeti carries another kind of inheritance, written into the movements of animals across grassland. Its great migrations depend upon seasonal rainfall, grazing grounds, rivers, volcanic soils, and the shape of the Eastern Rift landscape. Geological change works across all of those elements at once. Fault movement can alter drainage, uplift can redirect rivers, and volcanic activity can renew some soils while burying others. Across geological ages, these changes could fragment routes that animals have followed for generations. The migration itself may persist in altered form, yet the particular landscape that supports it today will not remain fixed. Human communities face a much shorter and more immediate relationship with the same forces. Around 150 million people live within the broader Rift region, across cities, farms, villages, and transport corridors. Their descendants may encounter more active faults, volcanic eruptions, ground subsidence, and damaged infrastructure as the rift continues developing. Geological change, measured in millions of years, still has consequences that arrive within a human lifetime when a road cracks, a settlement shifts, or a volcanic field becomes active. Even the places that preserve our own origins are temporary. Hadar, Laetoli, Olduvai, and the Turkana Basin have yielded fossils because erosion, sedimentation, and volcanic activity continually rearrange the surface. Those same processes can eventually bury valuable layers beneath new deposits or break exposed fossils apart. A site that survives for millions of years remains vulnerable to the next turn of the geological cycle. There is something deeply characteristic in this exchange. A rising landscape can create new habitats while destroying older ones. A deepening basin can preserve sediments while drowning ecosystems above them. When an ocean occupies land, the soil, rivers, forests, and freshwater communities beneath it do not travel onward as preserved pieces of the old world. They become part of the geological record. The rift, therefore, leaves behind more than a new boundary between continents. It carries a long succession of endings woven into every beginning, with biological worlds disappearing as physical landscapes are transformed. The planet continues its work through replacement, and what survives becomes part of the evidence from which another age will someday be read. There is a strange patience in the life of an ocean. The water may appear permanent to human eyes, yet the floor beneath it belongs to a much longer cycle. A new sea begins as a fracture in continental rock grows into a spreading basin and eventually becomes old enough to return its crust to the planet that made it. Oceanic crust carries heat away from the mantle as it moves outward from a spreading ridge. Cooling causes the rock to contract and become denser. Far from its birthplace, some of this heavy crust can bend downward at a subduction zone and descend into the mantle. The process helps draw neighboring plates toward one another, gradually narrowing the ocean between them. A basin that once separated continents can therefore become the space where those same continents eventually meet. The ocean created by Africa's division would follow this broader rhythm. Its early floor would be young and warm, while later crust farther from the ridge would cool through tens and then hundreds of millions of years. After roughly 200 million years, sections of oceanic crust can become old and dense enough to participate in large-scale subduction. The basin would begin its long return, while the continents surrounding it slowly change position. By approximately 200 to 250 million years from now, geological models suggest that Earth's continents could gather into another supercontinent. The precise arrangement remains uncertain. One model places much of the land around the Arctic, another closes the Atlantic and brings the continents together around that region, while another allows Australia and Asia to unite before the Americas complete the gathering. Their names differ, and their maps differ, yet each describes a future world in which today's separated continents have become neighbors again. The fragment leaving Africa today would have a particularly long journey. The Somalian plate, carrying Somalia, Djibouti, eastern Kenya, and eastern Tanzania, would continue moving eastward as the new ocean widened. Over immense spans of time, that fragment could encounter land masses now separated from it by entire ocean basins. Coastlines would disappear, mountains would rise, and familiar seas would become geological memories recorded only in rock. The Ethiopian highlands would travel through this transformation as well. The ground associated with Lucy, volcanic landscapes, and the great fractures of the rift would become part of a geography impossible to recognize from the present map. In 250 million years, the highlands might stand within an entirely different continental arrangement, surrounded by mountains, inland seas, or distant coastlines, shaped by processes already beginning today. Supercontinents also change the planet's climate, ocean circulation, and interior environments. When enormous land areas gather together, continental interiors can become far more isolated from ocean moisture, while new mountain belts alter winds and rainfall. The surface becomes a different world, even though the same rocks continue their journey through the cycle. This is the deeper rhythm beneath the African split. Continental separation and continental reunion belong to one continuous process, unfolding across hundreds of millions of years. A rift can open a sea can mature into an ocean can eventually disappear into the mantle. Across each immense interval, the planet redraws itself, carrying fragments of older worlds into arrangements that have never existed before. A map can make the continents appear fixed, as though the ground beneath every city were a finished surface. Along the East African rift, that impression begins to dissolve. The crust beneath the region is only about 19 to 40 kilometers, which is about 12 to 25 miles, thick, with the most active rift zones toward the thinner end. Far below, the mantle is hot enough to deform and flow over geological time. Every road, building, field, and boundary occupies a temporary position on that moving surface. The borders between Kenya and Tanzania, Ethiopia and Djibouti, or Rwanda and the Democratic Republic of the Congo are lasting agreements between people, while the rocks beneath them continue responding to heat and forces that operate independently of maps. The line survives through human memory, even as the landscape beneath it follows another rhythm. Human settlement has always been drawn toward places where geology gives something valuable. Rift valleys gather water, volcanic eruptions renew soils, and fractured rock can allow heated water to circulate close enough to the surface for geothermal energy. Lakes formed within tectonic basins support fisheries and agriculture, while mineral deposits created by volcanic and hydrothermal activity provide materials that become part of local economies. The same processes that create hazards also produce fertile ground, accessible water, and useful energy. Across a human lifetime, these benefits can outweigh dangers that unfold on a geological clock. The Afar people offer one of the clearest examples of this relationship. Communities have traveled across the Danakil Depression for centuries, working with a landscape shaped by salt, heat, lava, and evaporation. The region reaches about 122 meters, which is about 400 feet below sea level in its lowest areas. Conditions there can be severe, yet the salt beneath the surface has supported trade and livelihoods for generations. Blocks cut from the salt floor have moved toward markets across the highlands, turning an expression of geological change into something practical and valuable. That relationship reaches deeper than economics. People adapt their routes, settlements, work, and traditions to the character of the land around them. A landscape that seems hostile from a distant viewpoint can become familiar through generations of observation. Hazards are recognized through experience, resources are gathered according to seasonal patterns, and movement follows the places where water, pasture, and mineral wealth can be found. The longer view changes the meaning of that stability. A road may be rebuilt after a rupture, a settlement may shift away from a hazardous slope, and a damaged field may recover. Geological movement, however, continues accumulating changes that cannot be negotiated away. What appears permanent during one generation can become temporary when measured against the life of a rift. Its deepest lesson is measured in generations. Stability is something people create together, even when the ground beneath them never stops changing. The rift therefore reveals a tension woven through human history. Civilization seeks permanence, building homes, roads, cities, and borders that can outlast individual lives. The ground offers no such promise. It stretches and breaks, rises and sinks, while people continue making plans upon it. For the communities living here, geological motion is more than an abstract force deep underground. It is part of the setting in which livelihoods are shaped, decisions are made, and generations learn where they can safely place their feet. Before human eyes learned to read the language of rocks, continents had already been separating for billions of years. The Atlantic Ocean opened while forests spread and vanished, while creatures evolved and disappeared, while no mind existed that could place those changes within a planetary story. South America and Africa drifted apart. The Indian Ocean widened, and new crust rose between them without a witness capable of measuring the movement or giving it a name. Earth had been reshaping itself for 4.5 billion years before a species appeared that could understand geological time. Life was present through much of that history, sometimes in astonishing abundance, yet the scale of continental motion remained outside the reach of every living mind. A mountain could rise through generations, an ocean could widen beyond any lifetime, and a coastline could change beyond recognition, while the organisms living there experienced only the immediate world around them. The East African Rift occupies a rare place in this history. Here, a continental separation is unfolding, while one species, on the surface, can recognize the process itself. Humans can measure the stretching of the crust, map earthquakes, analyze volcanic gases, and compare observations across decades. The valley that helped shape human evolution has become a place where its own geological transformation can be recorded with extraordinary precision. Above the rift, the global positioning system allows instruments to detect movements measured in millimeters. Radar interferometry can compare repeated images of the ground from orbit, revealing subtle changes in elevation and shape. Seismometers register vibrations traveling through the crust, while samples from deep drilling preserve chemical evidence of the materials moving through the system. Each method approaches the same restless landscape from a different direction, turning motion too slow for ordinary perception into something measurable. The connection reaches further into human history. Geological changes in East Africa influenced climate and habitats, placing new pressures on early hominins. Upright walking became one part of that evolutionary story. Freed hands could carry objects, shape tools, and eventually participate in increasingly complex technologies. Across immense spans of time, those developments led to writing, mathematics, engineering, orbital observation, and instruments capable of detecting movements far smaller than a human step. There is something precise in that chain of events. The rift did not produce humanity in any direct or purposeful sense, and human evolution cannot be reduced to geology alone. Climate, ecology, chance, competition, and countless biological changes all contributed. Still, the landscape formed by tectonic forces became part of the environment in which our lineage developed. Today, descendants of those early populations can place instruments above the same region and measure the ground changing below. The rift itself has no awareness of this observation. Its rocks respond to heat, pressure, gravity, and the movement of material within the planet. They do not recognize satellites passing overhead or scientists studying patterns in their motion. The knowledge exists entirely within the minds of living observers. That makes this moment unusual in Earth's long history. A geological process is unfolding, and one branch of life has become capable of understanding that it is happening, recording its movement, reconstructing its past, and imagining its future. The planet has been changing since its beginning. Only now does something within that changing surface have the ability to notice. A fracture in the Ethiopian desert can look like an event made for human history. In 2005, a fissure roughly 35 miles long opened across the Afar region during a brief episode of intense volcanic activity. Hundreds of earthquakes accompanied the movement, and the ground opened in places where roads, fields, and familiar paths had seemed permanent. From above, the scar could be traced across the landscape. From the ground, its dimensions belong to another scale. Geology gives the same event a different meaning. A fracture of this kind is part of the ordinary work performed when continental crust stretches. Rock breaks, magma rises, faults shift, and the surface adjusts. Similar episodes have occurred throughout the long history of Earth, accumulating one small change after another until continents become oceans and old oceans disappear. The individual movement may be brief. Its significance emerges only when millions of such movements are placed together. That difference in scale reaches into the future of the East African Rift. The opening of a new ocean will eventually alter coastlines, reshape drainage systems, separate habitats, and transform lands that are familiar today. Entire ecosystems may disappear as freshwater environments encounter marine conditions. Rivers will find new routes, mountains will rise and erode. Land that now seems fixed will become part of a geography with different proportions and different boundaries. Earth has carried out this kind of work many times. Oceans have opened where continents once touched, then vanished as their crust returned to the mantle. Supercontinents have gathered scattered landmasses into enormous assemblies before breaking apart again. Mountain belts have risen through collision and later been worn down until their roots became part of the crust. Ocean floors have descended through subduction before animals with backbones had appeared. Volcanic provinces once covered regions comparable in area to modern nations, only to be reshaped by erosion and tectonic movement. Across these immense cycles, there is no evidence that the planet distinguishes between beginning and ending. Heat escapes from its interior, rocks respond, crust is created and consumed, and gravity helps guide the movement. The process has no preferred coastline, no attachment to a particular mountain, and no memory of the landscapes that existed before. What seems monumental to a civilization can be only another adjustment within a planetary system operating across hundreds of millions of years. Something else, however, belongs to the present moment. For the first time in Earth's history, a species living through continental change can measure its speed, reconstruct its earlier stages, and place its current movement inside a history spanning billions of years. Human beings can watch earthquakes on instruments, compare satellite observations, date volcanic deposits, and follow the gradual separation of land with mathematics. A human lifetime occupies only a brief interval within that transformation. That awareness creates an unusual contrast. The rift itself requires no witness. Its rocks continue responding to heat and pressure whether anyone records them or not. The significance exists within the observer, within a mind capable of connecting a fracture measured in miles with an ocean measured in millions of years. The movement is ordinary for the planet. Understanding that movement is extraordinary for the life upon it. A continent can divide without knowing it is dividing. For the first time, something living on its surface can know. A fracture runs across northeastern Ethiopia, a scar in a landscape that appears fixed from a human distance. It stretches for roughly 35 miles, yet its importance cannot be measured by its visible length. The crust around it is being pulled apart, and molten rock has risen through fractures where continental material is beginning to give way to the structure of an ocean basin. The transformation is underway long before any sea can be seen. Near this changing ground, Afar communities continue their lives through work shaped by the land. Camels carry blocks of salt across the Danakil Depression, following routes that connect settlements and markets. Nearby, Erta Ale maintains its persistent volcanic activity, its lava lake offering a glimpse of material arriving from deep within the planet. The landscape is severe, yet human life has found practical rhythms within it, using the resources created by the same geological forces that continually rearrange the surface. Geological time gives this place another identity. The depression that holds salt today is part of a continental region being stretched toward eventual marine conditions. Models suggest that, over millions of years, continued extension could allow seawater to enter and establish a new ocean basin. The exact timing cannot be known with precision. 10 million years from now, the landscape may be profoundly different. 50 million years into the future, coastlines could occupy places that are currently dry land. Hundreds of millions of years later, the ocean itself could become part of another cycle of opening and closure. Every future landscape begins as an ordinary surface beneath present feet. A desert can become a shoreline. A volcanic highland can become an island. An ocean can widen until continents, once separated by distance, are eventually drawn together again. None of these transformations arrives as a single event. They accumulate through countless movements, each one too small for a human life to contain, until the accumulated changes become impossible to overlook. There is a strange intimacy in knowing this while standing on the ground itself. The same region preserves evidence of early human ancestors, while its rocks continue participating in a process that began long before our lineage existed. We can place instruments across the rift, record earthquakes, measure crustal movement, and compare observations across generations. For a brief interval, a living species has become capable of following the transformation of its own planetary home while that transformation is still occurring. The knowledge will not alter the movement. The crust will continue responding to heat, pressure, gravity, and the circulation of material within Earth. If every human observation disappeared tomorrow, the rift would continue widening according to the same physical laws. Its future would remain beyond the reach of any witness. For now, though, there are witnesses. Somewhere beneath northeastern Ethiopia, the planet is still pulling itself apart at a pace almost imperceptible to the human body. A desert remains a desert for the length of a lifetime, even as its deeper structure moves toward another identity. The crack is still growing. It carries no intention and offers no promise. It is simply part of Earth's continuing motion, while for one brief moment, something living upon its surface can understand that the ground is changing, recognize the direction of that change, and place its own existence inside the immense passage of planetary time.